Thank you. Yes. So thanks the organizers for the invitation, and thank you for coming. Yeah, so my talk is going to have two parts. In the first part, I'm going to talk about this Hilbert scheme of points in affine n space. So yeah, this is all joint work with Joachim Jelisiejew, Denis Nardin, Burt Totaro, and Maria Yakerson. Yeah, the second part will be kind of most independent from this one. So I will be talking about algebraic probabilism and what this has to do with these Hilbert schemes, which was our original motivation for looking at these Hilbert schemes. But I mean, the Hilbert scheme, I think, is an interesting object by itself. So since we computed something about it, I tell you about it. Okay. Yeah, so let me first recall the definition of this scheme. So one considers a functor from commutative rings to sets, which takes a ring R to the set of subschemes of the affine n space over R. Such that the map from Z to spec R is finite flat of D with D. Yes. Yeah, or if you prefer to remain in the world of commutative algebra, then this is commutative R algebra, such that the underlying R modules is finitely generated projective of rank E, together with a surjection from a polynomial ring n part. Yeah, and I guess it goes back then to Grothendieck that this functor is represented by a scheme, and I mean in this case it's the quasi-projective scheme. Over the integers, but you could take your favorite base field. Yeah, so this is quite an interesting scheme. Of course, you can make this definition also when you replace a affine space by some other thing. But already in the case of a affine space, it's already extremely complicated geometric object. And so let me mention the following theorem of Joachim Jelisiejew, the recent result that if n is at least 16, then this scheme satisfies so-called Murphy's law. Yeah, so this is a term devised by Maria Yakerson. So, but basically, what this means is that any singularity type can be found in this scheme. So it's maximally singular scheme. Yeah. So as soon as, so for example, the Hilbert scheme of points in A16 has this property. Yeah. So it doesn't even hopeless to say much. In general about this.
You need to take the union of all D.
Yeah, so here, yeah, you have to the union of all D. So D is arbitrary. But okay, you can still, ask a bunch of questions about this. So for example, can you compute the cohomology of this thing? Or can you compute the motive of this scheme? These kinds of things. So there are some classical results there in some edge cases, which are tractable. So for example, one case is when n is equal to 2. So when n is equal to 2, the scheme is always smooth. Using the smoothness, we can actually compute the motive fairly easily using this So the point is, so you have an action of GM on this. I mean, you can let GM, the multiplicative group, act on A2 by scaling linearly. And there's induced action on the Hilbert scheme of points on A2. So this is not a projective schemes, but nevertheless, if the attractors will exist. So if you go towards 0 in GM, then the limit point on the Hilbert scheme will exist. It will be some fat point at the origin in A2. And if you choose, if you choose the scaling in the X and Y direction to be sufficiently generic, then the attractors for this GM action are going to be isolated points. And whenever that happens, then and your thing is smooth, then there's a theorem. I mean, this follows from this Wernicke-Birla decomposition or stratification that the motive of such a thing is always a pure Tate motive. Basically, because if you look at all the points that flow towards a given attractor, this will be some affine space. Yes, you get a stratification of this variety by affine spaces, and then it's easy to compute the motive. And it's always a pure Tate motive. So the motive of Hilbert scheme of points on A2 is pure Tate, and yeah, I mean, you still have to work out what the dimensions of these cells are and so on, but this you can do. And so you get an explicit answer. Yeah, another case where you can compute the motive would be if D is 3 and N is arbitrary. So this is also a case where this is smooth. So again, then the same Wernicke-Birla result would also apply, for example, to tell you. But okay, in this case, it's also more elementary. You can compute directly what the motive is. It's also a pure Tate. Okay, but beyond these two cases, somehow, then this is definitely not smooth. And then, yeah, so this Wernicke-Birla result, I mean, you can still look at these GM actions and you will still have attractors that exist, which are isolated. But if the ambient scheme is not smooth, then these cells of points flowing to an attractor are not going to be affine spaces anymore. There will be more general singular cones. So this doesn't really help if you want to compute the motive. Okay. So, but what we notice is that if you let this N go towards infinity, then you can actually say something about the motive of this and more general things. So the first part is the limiting case. So you look at the Hilbert scheme of points in A infinity. And it turns out that this is A1 homotopy equivalent to the moduli stack of vector bundles of rank D-1. And of course, I mean, from a motivic perspective, this is a very simple object. In particular, we know very well what the homology or what the motive of this object is. And it's the pure Tate motive. And I mean, it's the same as the motive of this. Yeah, so that means that up to A1 homotopy, somehow this object becomes very simple as n goes to infinity. And the second part of this theorem is a stability theorem, which says that, well, if n is large enough, well, you can still say something about the cohomology of this object in some range. So, one way to say this is to look at this inclusion of the AN into the A infinity. And then this morphism will have some connectivity property. So which I put in quotes because I don't want to precisely define what that means, but it's n minus e connected in some A1 homotopical sense. And yeah, instead.
There's a question from the chat. Could you mention again what vec D-1 is?
Yes, vec D-1, this is the moduli stack of rank D-1 vector bundles. Which you could also denote by EGL -1. So the Dasrank stack of this algebraic group. And in A1 homotopy theory is also a standard result that this is also A1 equivalent to just the Grossmanian of D-1 dimensional plane. So if you want to have an honest scheme here instead of a stack, you could just take this Grossmanian. Okay, now, yeah, so as I said, I'm not saying what this means, but instead, let me tell you what some consequences of this connectivity are for some standard cohomology theories to give you an idea. So, for example, so let's look over the complex numbers, just ordinary cohomology, then this would be saying that if I look at the cohomology of this over the complex numbers is a polynomial ring over the first, the D-1 Chern classes. And well, there's going to be a map from this to the cohomology of this Hilbert scheme. Now I look at the complex points of this, and yeah, so this connectivity translates the fact that this is an isomorphism in degrees less than or equal to 2n minus 2d plus. Okay, it's some number, but yeah, and here Ci has degree 2 times I in this polynomial ring. So this is the Chern class. Yeah, so we get a result like this, and then let me also mention you can also take, instead of complex points, you can take the real points, so the real numbers. So and then if you take cohomology with F2 coefficients, then you have the stack now. Cohomology is a polynomial ring on the Schlieffler-Whitney classes. Now look at the real points of this. This is an iso in degrees. That's equal to 10 minus d. And yeah, finally, let me also say what happens in motivic cohomology, because then it's a little bit different. So motivic cohomology of this, again, why it's basically this, except you have to replace z by the motivic cohomology of the base field. Yeah, let's say that we over field. So so you have this motivic cohomology ring of the base field, which is a bigraded ring. Chern classes, motivic Chern classes. And this maps to cohomology of a Hilbert scheme. And now this would be an isomorphism in weights less than or equal to n minus d plus 1. The weight refers to this weighting here. So now this weighting here can be arbitrary, but as long as this weight is less than or equal to n minus d plus 1, this is a nice. This is a little bit different than the previous two examples, but somehow, I mean, this is hidden in what exactly I mean by this n minus d connectivity in this A1 homotopy context. Yeah, but it has all these consequences. Okay. So I did want to say something about the proof of this, because yeah, this proof is actually quite elementary in some sense, so it's very simple. Yes, so what about this first statement that says that Hilb of A infinity is just vector bounded, yeah? So let me just say something about this proof. So here what we do is yeah, so there is, well, I'm going to describe a map from here to here, but so this map will be the composition of two maps. The first thing I do is I have a map to the stack of just finite flat schemes of DBD. And secondly, we have a map to vect D minus 1. So, oh, sorry, this should be, it should be n, but here it's infinity. So this first map is just a map that forgets the embedding in A infinity. Yeah? So we find that flat scheme of degree D, which is embedded in A infinity. So just forget this embedding and you get just this finite flat scheme. The second map, so it's not just forgets. I mean, you can, if you're over an affine scheme, yeah, so this is a finite flat R algebra of degree D. So I mean, you can just forget the algebra structure, and then it's a vector bundle of rank D. To get one of rank D minus 1, what you do is you, so it's A over R, finite flat algebra of rank D, and I send it to A modulo R. Yeah? So now this is a finitely generated projective. Yeah. Sorry, I did not realize this. I hope this is clear. Yeah, so this is a quotient, and this is a finitely generated projective R module of rank D minus 1. Okay, and now the claim is both of these maps are somehow A1 equivalences. And so let me look at this first map first. So this is, you just forget this embedding in infinity. So the idea is somehow the data of an embedding in an infinite dimensional affine space should be A1 contractible data. This is the idea, and this is also exactly the proof. So, so what are the fibers of this morphism? So if I pick a point here, so this is some finite flat scheme Z, and the fiber here is the space of embeddings of this Z inside in A infinity. So this is back. And now, yeah, so this space here turns out to be A1 contractible. Yeah, so this is something which is similar to what happens differential geometry as well. Yeah, if you look at the space of embeddings of a manifold, compact manifold into infinite dimensional Euclidean space is contractible space. I guess this is the Whitney embedding. Yeah. So there's an analogous result here. And so how do you prove something like this? Well, I mean, topology, what you could do is, well, show that any map from a sphere is null homotopic. And it turns out in this A1 homotopic theory, there's a similar thing you can do. There's a similar criterion for A1 contractibility. So, but in this context, the spheres would be something like the boundary of AN. So this is, what this is a union of all the coordinate hyperplanes in AN together with one additional plane, which makes like a boundary of a simplex. What's easy to prove is that if you have any morphism from here to here, then you can extend it to the whole affine space. Yeah, so this is like inclusion of the sphere in the disk. And there always exists an extension like this. And well, the reason this is easy to prove is that it has nothing to do with this specific situation. If you have any kind of closed embedding between affine schemes, you can extend from here to here. And this automatically implies that this thing is A1 contractible. So this is how you prove these kinds of things. And I mean, this is completely elementary thing. I mean, it's an exercise which you can solve, that you have this lifting property. Okay. So this is why this map is an A1 equivalence. In fact, this proves something slightly stronger. It really proves that this map is universally an A1 equivalence. So it remains an A1 equivalence after any pullback of it. This is A1 equivalence. So for example, if you look at some substack of this stack here, this corresponding subscheme of the Hilbert scheme, and then the map will still be an A1 equivalence. Yeah. So later on, for example, I'm going to talk about the substack here of local complete intersections. So you can also use this argument. Okay, and for the second one, so this one is a different type of argument. What we do is we consider a morphism in the other direction. Namely, if I start with finitely generated projective module of rank d-1. How do I get an algebra where I can take the square zero extension? R plus T. So this is now an algebra of rank D. And of course, if I start with P, I take this square zero extension and then take this quotient, I get P back. But in the other direction, that this is not the case. So if I start with an algebra, I just forget some of the algebra structure, take this quotient, take the square zero extension. Okay, well, I get completely different algebra. But the point is this composition is still going to be a one homotopic to the identity. And the way this works is via the Rees algebra. So I'm looking now at this composition from F flat D to F flat T, which sends A to the square zero extension R plus A mod R as a module. And so this is A1 topic to the density via so the Rees algebra, something you can do whenever you have kind of a tilted ring. So in this case, it's just R plus direct sum of A T to the I, so as a subring of this polynomial ring. And this thing is a finite flat. Yeah, like this. This is a finite flat algebra with this polynomial ring of rank D. And if you look at if you extend scalars to t equals 0 or t equals 1, you will get respectively the original algebra and this algebra. So this is exactly what an A1 homotopy is between this morphism and the identity. Are there any questions about this?
So how important is that it's A infinity or other than other big, right?
Yeah, it seems pretty important. I mean, if you try something with like B infinity or something like this, then this argument would not work.
So this first diagram, this lifting property is not completely obvious. You really use this.
Yeah, you really, yeah, I mean, yeah, you really make this explicit. What happens here, yeah, just in terms of like commutative algebra. I mean, this just means that you have a set of generators, right, for the structure sheet as a ring. But yeah, I mean, because somehow the conclusion is somehow very strong, you just get an A1 equivalence. I mean, if you ask for a weaker conclusion, like when an equivalence of motives or something like this, then maybe I could imagine that some argument with some other variety here would still work, yeah. But having an A1 equivalence is somehow very strong, so you don't have that many tools to establish that something's an A1 equivalent. So I think it's really, yeah, it will be really hard to replace this lesson. Yeah, so let me just start by talking about what happens in topology. When people talk about cobordism, I mean, they imagine usually this picture. It's a pair of pants picture, which describes a cobordism from this union of two circles to this one circle here. The way I like to think of such a cobordism is that this is really a path from these joint unions of two circles to this one circle in the moduli stack of, well, in this case, of one-dimensional manifolds, one-dimensional smooth compact manifolds. We call this moduli stack MFD sub 1. Yeah, so this is really what cobordism are. They pass in these things, and yeah, so in algebraic topology, one is interested, well, manifolds up to cobordism, but you can do, if you think about it this way, this tells you that manifolds up to coordinates is just some of the connected components. I mean, the path connected components of this stack. Yeah? But of course, what you can do is instead of just consider the path connected components, you can consider the whole homotopy type of this thing, and this is what's called the coordinate space. And so this is some subspace where some of the points are these one-dimensional manifolds in this case, and then a path in this space is a coordinate, and then you have a homotopy between paths, which would be coordinates between coordinates, and so on.
That's just an intuition, or is this like an actual fact? Like how do you deal with like singularities that might occur during
yeah, so I guess this is an intuition, and you can transform it into a fact. So indeed, there's an issue even to talk about this moduli stack, I guess, because the issue is you cannot really pull back. I mean, the pullback of smooth manifolds is not going to necessarily a smooth manifold. Yeah, it is you have a non-transverse thing, but this you can resolve by using kind of derived manifolds. So if you use derived manifolds, I mean. Then this does become a fact, and then everything I say is actually precise. Yeah, so cobordism space. This is somehow another name for the homotopy type of such a moduli stack. Moduli stack of smooth manifolds of some type, and there's lots of variations. You can look at manifolds with some structures like oriented manifolds typically, so you have all these variants of coordinates, and topology. What one proves is that these coordinate spaces, they are somehow they're infinite loop spaces, and I mean they're the constituent space of some spectra, and these spectra are somehow easy to construct independently of this geometry that's called the Thom spectra. So one proves things like if you look at the Thom spectrum MO, then it's underlying, so it's infinite loop space, so that's like the zero space in the spectrum is well, it is exactly this coordinate space of well, let me just say that it's homotopy equivalent to this moduli stack of zero-dimensional smooth compact. What O does, and then there's all these variants of this, like mu. Mu this corresponds to putting a stable complex structure on the manifolds. And this is a moduli stack of, well, zero-dimensional manifolds with stable complex structure. And then I mentioned another example, which is the sphere spectrum itself. So the sphere spectrum is also one of these Thom spectra, and it corresponds to zero-dimensional manifolds with a stable framing. Yeah, so this is and I mean, okay, so this is just a zero space of this, which is why you have zeros here. But if you look at the other spaces in the spectrum, then you get other numbers. So that's how this works. So in some joint work with Eldon Almanzo, Adil Khan, Vladimir Sosnilo, and Maria Yakerson, we obtained some analogs of these results in algebraic geometries. So and Yakerson. Yeah, so you have, right, so in motivic homotopy, one has analogs of spectra like these things. These Thom spectra are also out there, and the main one is so-called MGL spectrum, which is, I guess you should think of it as some algebra geometric refinement of this MU spectrum. I mean, this MU spectrum is something which is built out of Thom spaces of these tautological vector bundles and Grassmannians. Yeah, I mean, Riemannians are smooth projective varieties, and so everything is it's algebra geometric. And if you remember that, then you would get this kind of motivic spectrum MGL. Oh yeah, so that this is now, I guess, E1 equivalent to, yeah, so I write bar 0 for kind of moduli stack of compact, well, I guess proper zero-dimensional varieties. But here I look at the local complete intersections. So proper local complete intersections. And what I still have to do here is also take some other group completion of this. So this is a monoid on the disjoint unions of things. Yeah. And I have to take a group completion into this, and then I get this infinite loop space of this MGL spectrum. Yeah, and then, I mean, so I mean, there's also analogs of this for other kinds of dumb spectra. So let me just mention this one for the sphere spectrum. Then you get, so now there's a motivic sphere spectrum. You have something, I mean, you can define what it means, what the stable framing is on a scheme. And then, so you look at this moduli framed, stably framed zero-dimensional thing. And again, you have to take the group completion of this, the disjoint. Yeah, so this is very similar to this. I mean, there's one obvious difference which you notice is that you have to take group completion here. This you don't have to do in topology, because in topology, I mean, if you look at these as monoids on the disjoint unions, then I mean the homotopy types are already groups. For example, I mean, this is very easy to in this case, very easy. So I mean, if you have a point, so this is one of these zero-dimensional things, and another point, then picture like this is a cobordism, right? From point plus points to the empty. To the empty manifold, and the empty manifold is a zero object. So, yeah, so this is in fact the true torsion thing. Everything is additive inverse to itself in this thing. This is not so here. Yeah? So these are more interesting in that case. These are not true torsion, but still you can prove that everything has an additive inverse up to cobordism. Yeah? And I mean, this does not work in algebraic geometry, yeah, because I mean, you cannot have a picture like this. I mean, a picture like this really represents something with some proper map to a line, A1. And yeah, it's not possible. Algebraic geometry, you cannot have a fiber like this, which is okay, so this is one difference. Yeah, and then should also mention now that these things, yeah, so now I write bar 0 for this, but another example of this was the stacked finite flat schemes that I had before. So, which had this interpretation in terms of a Hilbert scheme, and there's a similar thing here. So you can write these things also, and then these are also A1 equivalent to some suitable Hilbert schemes of points. So in this case, the effect of local complete intersections. Yeah, and I mean, then you still need to take this group. Here, there's also a kind of Hilbert scheme of framed points. And yeah, so a framing of a point in the Hilbert scheme here would mean trivialization of the normal bundle of the embedding. That's what a framing means concretely. So in fact, both of these things are smooth schemes. Yeah? So this is the LCI locus in the Hilbert scheme. The Hilbert scheme is singular, but the LCI locus is a smooth open subscheme of that. And this one is kind of a torsor of this one for some smooth algebraic group. So. Yeah, so maybe so what I explained in the first part with the equivalence between field and these vector bundles has kind of the following consequence. Which is that the algebraic gate theory spectrum also has a description, kind of a cobordism type description like this. So yeah, maybe I write it in this manner. The analogous to this, so this is a metric spectrum KGL, which represents algebraic gate theory, and This would be A1 equivalent to this moduli stack of finite flats. So take a group completion of that. Yeah, and then a little bit later, with Nardin, Jelisiejew, Nardin, Yakerson, we also proved analog of this for Hermitian K-theory. And for Hermitian K-theory, this looks like the infinite loop space of this Hermitian K-theory spectrum is the group completion of some moduli stack of oriented finite Gorenstein algebra. But I think I don't really want to go into the details of this. So, but let me just say something about this. I mean, okay, this looks a very abstract result, but I mean, maybe I can say something more concrete. What is it saying about K-theory? So he's saying that if you have, in particular, he's saying something like this. Strange. If you have some commutative ring, then A0 R, you can kind of compute it as you look at finite flat R algebras up to cobordism. Modulo this cobordism relation is very naive relation. This is very naive A1 homotopy relation. So this is a cobordism is something which is finite flat over A1, and that's a cobordism between the fibers of A0. Very naive relation. And then it's the group completion of this. Yeah, so I mean, this is similar to some of the usual definition in terms of vector bundles, but you use finite flat algebras instead and cobordism. So obviously it's more complicated than the description in terms of vector bundles, but somehow, yeah, I don't know. This is what comes out of this, for example. And yeah, this is really a commutative algebraic description of algebraic K-theory. This does not make sense for non-Hilbert theory, for example. And yeah, this is just K0, which is somehow the pi zero of that space, but actually we give a description of the whole K-theory space here as the cobordism space of this finite flat tower algebras. Yeah, so let me mention, include in this conjecture of Mike Hopkins, which was kind of the, which was the motivation for us to try to think about what the motives of these Hilbert schemes were, for example. Because, well, Mike Hopkins tells you, if you can somehow compute the motives of some Hilbert schemes, then you get some nice things. Namely, you get some interesting results about classifying vector bundles on complex affine varieties. So this conjecture. Which is called the Wilson space hypothesis, and it says that the motives of the spaces of this algebraic cobordism spectrum and and here I really mean the integral motives. Yeah, this is not the rational conjecture. Well, it's also in particular a rational conjecture, but you really need some of the integral version is a pure Tate motive. Yeah, and for so this conjecture, this is something that happens in ordinary algebraic topology, for example, and it's already a strange phenomenon there. If you look at this infinite loop space of the spectrum mu. So what does it mean to be pure Tate in topology? Well, the obvious analog of pure Tate in topology means that the homology is concentrated in even degrees. This is what pure Tate means. So mu is a spectrum that has this property that its underlying space has homology concentrated in even degrees. And of course, its homotopy groups is also concentrated in even degrees because this is a computation of the complex cobordism ring of a point. So yeah, it's in topology, this really very, very strange space that's just both the homology and And the homotopy is constrained in even degree. That's a kind of rare property with a lot of nice consequences. But so anyway, this is kind of based on this topological fact, which was proved by Wilson, which is why it is called the Wilson space of part of this. And now when n is equal to 0, this so this is the motive. This is where this Hilbert scheme comes in. This is the motive of I guess I could write it like so just countable disjoint unions of copies of this LCI Hilbert scheme infinity, and also kind of let also the degree go to infinity. So the motive for n equals 0, this motive is the same as countable direct sum of the motive of this. So this is why somehow we were interested in the motive on this motive and trying to prove that it's a pure Tate motive. As I mentioned, one nice thing about this LCI locus is that it actually is smooth. If you remember what I said about Bialini Kidrula decomposition at the beginning, this is something that works for smooth varieties, so you might be happy about that. But of course, it's not so simple. So the issue is that, I mean, you see that GM actions and these Hilbert schemes. The problem is that the attractors don't exist now, because I mean, if you degenerate some local complete intersection, then it will typically not be a local complete intersection anymore. So yeah, so also Bialini Kidrula does not apply. And in fact, I mean, if you look at some low degree examples, you can see that this LCI Hilbert scheme. So what would be the first example? I guess Hilb 3 LCI in A2. So this, I mean, this is low enough that you can compute everything you want, and the motive there is not pure. It's mixed state, but it's already not pure. So somehow you cannot hope to prove the pure Tate nature of this by just proving it for all the finite cases or something. It's kind of a subtle conjecture, but okay, sorry, I'm out of time. I just mentioned that the consequence of these conjectures is that on smooth affine varieties of the complex number which are cellular, then every topological vector bundle has unique algebraic structure. So you have a bijection between algebraic vector bundles and topological complex vector bundles in this situation. So I mean, this is totally non-obvious consequences of this, which comes out of computations with like unstable motivic Adams-Novikov spectral sequence and things like this. But this is somehow, I think, also was one of the motivations for Hopkins to make this conjecture.
Okay, so there are no questions, and let's thank Marc again.